Alright, so we're looking at draw and analyze the following distance time graphs and displacement time graph. Distance is a scalar and displacement is a vector. So if I'm going from A to B and back to C, so I go from A to B and come back to C, I do this journey like that, and then I come back like that. Let's say this is at t is equal to 0, I'll call this t0, I'll call this t1, and I'll call this t2, like that. Then if I was plotting this graph of displacement against time, then this would be 0, this would be t1, and this would be t2, like that. This distance from A to B would be back like that, up to there, and then this would perhaps be C. So what you would have is, if it was at constant velocity, if it was at constant velocity, at t1 you're at B, so you'd have something like that, and then you would come back at t2, you would be over there. So that would be your displacement time graph if you were going at a constant velocity. You see, you've actually come down again. If this was a distance time graph, and I'll do the distance time graph in blue, then what would happen is that from t1 to t2 you would actually continue going up to there. So your graph would be like that, and then it would be like that. It would be adding on. Alright? It wouldn't be subtracting. So the final displacement is from A to C. That's your final displacement. That's that value over there. Your final distance is that plus that, which is that over there. So when you're dealing with distance time and displacement time graph, you can have your distance will always be adding on, your displacement may well be subtracting if it's going in the opposite direction. Now, coming back to, let's just work with displacement for the moment. So we've dealt with the difference between distance and displacement. Let's just go back to our displacement time graph, and there's a few things that we need to know about this. If I've got a graph like that, straight line like that, so this is in t1, and this I have got a distance s1. What would the slope of my graph equal? What would that slope, the slope of that graph, be telling you? Well, whenever we are dealing with slope, we are dealing with what we call rise over run. So this slope is measured in meters, and the run is in seconds. So when you're finding your slope, it's a meters divided by a second, or a meters per second. So the important thing to remember here is that the slope for a displacement time graph equals your velocity. Okay. Now, in this case over here, I had a straight line. So therefore my velocity in this case, my velocity is constant. I've got a constant velocity there. Okay? Constant velocity, because a straight line, your slope is the same. But if I had something like this, if I had something that went like that, alright, now you can see that your slope starts off at 0, and in the end it's going like this. So we can see that you're getting a changing slope, and therefore you're getting a changing velocity. This would be accelerated motion. You're getting acceleration taking place here. Alright? And this would be in an increasing velocity. Here we are starting off at 0. Our velocity here would equal 0. And here our velocity would equal something bigger. So this is accelerated motion. If I went like this, if I went something like this, this would also be a changing velocity. But here we are starting off with a velocity that's quite high, and we're ending off with a velocity that's just about 0. So here we are getting deceleration. So you can look at the shape of your graph and be able to see whether you got a constant velocity, which would be a straight line, where you get whether you're getting an accelerated motion or a deceleration that's taking place by looking at that graph.